Yeah,
don't
the
need
end
to
of
do
the
that
class.
and everything. I don't know if it's in
Yeah,
your
the end of
exact which
semester.
one. The polymer engineering, now they hear what you actually do might be, that might be worth it. You might wanna look into that. You, even if you audit it, if you're not worried about the grades, because that's the actual engineering of the polymer, because you guys are using that to like make these things. If there's anything self-assembly or you know the polymer, it's like you guys are making the polymers with these, the high temp kind of components.
Yeah, I mean, the thing is, like, we're making something, and you heat it up, and take it off, and heat it up, take it off, and eventually becomes a type of structure with the polymer, and then after that, you degrade it off.
Yeah, you just burn the polymer off.
Yeah.
Yeah.
Are you
And then-
working on cream?
I will be, yeah.
Oh,
I will be, so I'm gonna have to take that mechanical behavior class eventually.
oh, Dr. Raj.
Yeah.
I'm excited for that one.
Yeah. I don't know how to feel about it.
They said if we go to class, because he asks class things that he'll say in class specific questions.
I don't know, I mean, just trying to figure out the best course to take is like already stressful enough.
Are you still taking the combustion phenomenon class?
Now that if it's in the fall, then probably not, because I have to take a colloidal class, so I need to find something else to take in the spring.
Okay.
So I'm kind of searching right now.
There's a combustion class?
Yeah, he was saying that it, yeah, phenomenon combustion class. He's saying that it does, like it checks out the materials, and I was like, oh yeah, I'm gonna take something that's mechanical gear, that's my shit.
Yeah, so you're making bombs, right? Like,
Energy too.
no, that's not cool.
Look, we all know
We're
that
making
science
sure
is
things go boom.
explosions
Huh?
everywhere.
We're making sure things go boom. Professor, how was your day? You don't look
Boring.
as excited.
What's that?
You don't look as excited as you usually are.
Boring or busy? Boring.
At least that's it.
All right, so shall we start? We continue our topic the last time. I think we're still going to talk about the, so last time we talked about the equilibrium. First thing we talked about is the reaction equilibrium. Okay, that's the first thing. And we introduced the equilibrium constant Kp, right? And then we also mentioned about the pressure equilibrium. Okay, and we have not talked about the temperature effect yet, right? So we're gonna talk about it, right? So briefly, the reaction constant can be expressed in this way. Right? And specific to this reaction, we mentioned about reaction on viscosity, something like this, right? So we have 1 molar of A react with 1 molar of B and generate 2 molar of C. Okay? And then the reaction constant for this kind of specific case equals to the partial pressure of C squared, PA, partial pressure A. Okay? So that's the constant. And one thing I want to reemphasize is that here, what's the definition of, we call it the standard, the change of the standard Gibbs free energy. So this means the change of the standard Gibbs free energy means we have, for example, the ratio here is 1 molar, 1 molar, and 2 molar, right? So that is the delta G. So specific to this reaction, okay, we have 2 molar. That means the 2 mu C naught minus mu A. Okay? And that means in this case, the pressure is 1 atmosphere, and this one is 1 atmosphere. and this one is also under the pressure of 1 atmosphere. We do not consider reaction, we do not consider mixing, okay? We just put 2 molars of C and 1 atmosphere, and minus the chemical potential of the 1 molar of A under 1 atmosphere pressure, and minus pressure of B, chemical potential of B under 1 atmosphere pressure. That means they are fully separated, okay? You have 1 tank, 2 molar of C, you have 1 tank of A, and 1 tank of B, okay? We just minus. That's it. We don't mix. We don't trigger reaction, okay? So that's the definition of it, okay? So the reason we introduce this definition, this makes our job easier, right? Because as long as we know the chemical potential in this kind of standard situation, we will be able to know the chemical reaction, okay?
So if it's standard and we treat it as though it's not mixing?
No, we don't mix them. If you mix them, the entropy change. We don't mix, right? We don't mix at all, okay? All of them are separate. That's the definition.
So A and B are separated, and mixing of A and B is 2C, right?
Not mix, the final product.
Final product is.
You have 1 tank of hydrogen, you have 1 tank of chlorine, you have 1 tank of hydrochloride.
Mhm.
They are separate, no interaction.
So why do we need hydrochloric 1 tank? Because finally we are going to get it from hydrogen and
No,
chlorine.
no, no, we are not talking about the reaction process.
Okay.
We just know the final product is this one. And the precursor of this one, we need to calculate the change of the entropy.
Is just to know the state of the final product.
We just put the pure final product for the calculation, okay? You know what I'm saying? Because I mean, if you mix them together, the final product can be a mixture of hydrogen, chlorine, and hydrogen chloride, okay? But we don't care about what's left over there. When we calculate the delta G, we start from the pure hydrogen, pure chlorine, and pure hydrogen chloride. And we calculate the delta G in this case. And by putting delta G and know the temperature, we can calculate the reaction. You know what I'm saying? Is that clear to everybody right now? So in other words, as long as we know the starting material and the final product, we can calculate the parameters of reaction. Okay? But again, this one is only work for the gas. We're going to talk about the chemical reactions involve the condensed matter or condensed phase in this class, okay? But let's finish this one first. Okay, and for last time we also talked about pressure effect. And for example, if that means we just talk about pure gas, okay? Pure gas reaction. So if the final product lower the pressure of the system, so we can pressurize the system to move the reaction to the right side. Okay? If you produce more molecules and then the pressure of the system goes up, by reducing the pressure, we can move the reaction to the right side. Okay, this is what we're talking about. But what about temperature effect? Okay? We have not talked about temperature effect yet. Once again, so this one is the derivation of you call the standard heat free energy, right? But the reaction actually is defined by, last time we talked about the delta G prime, right? It's defined by delta G prime. It's not defined by this one, okay? I mean, you can calculate, but it's not defined by one. It's defined by this one, right? So by drawing the figure, we know this is Na, and on this end is 1, on this one is 0. Okay, we only consider 1 molar, okay? Then we have 2 effects, okay? One is the delta H. The other is the delta P. Because the reaction will just keep that constant temperature, okay? So we do not consider the pressure, at the beginning we don't consider the temperature change, right? And then we know that one. So this curve is the delta H, right? So at this point, it's just A plus B, okay? And at this point is the 2C, correct everybody? And then on the other side, we also need to consider change of the entropy. The change of the entropy looks like this, okay? And when we got pure C, the entropy is 0. And at the beginning, this one is just the entropy change due to the mixing, okay? After you mix A and B, the entropy drops, right? And then we combine these 2 facts together, and eventually you get something like this, okay? And the minimum point here, we find the equilibrium state of the reaction, okay? And also from this point, we can get this equation. But the question is, what if we change the temperature? What if we change the temperature, okay?
Due to the mixing, entropy decreases or increases?
The entropy increases,
But
but we have negative sign here. Okay, so let's briefly analyze what is the effect what's the effect of temperature change on delta G prime, okay, on delta G prime, okay? So we know that the entropy basically just because of mixing, okay, because it's configuration entropy. So this term typically doesn't change, right? It's just about mix the gas together, okay? It's not dependent on temperature, but since the Gibbs free energy change is proportional to minus T times delta S, if delta S doesn't change, the T changes, right? And then this part becomes longer, right? If you increase temperature, this part going down, this part moving down, right? This part becomes longer, right? Correct?
So this is TDS, we can consider this part as TDS.
Okay. Yeah. Okay. So that's one effect because the entropy change. Okay, but on this end, the entropy doesn't change. Correct? So you can see that as we change the temperature, we always have this part increase, right? So we know that if the change of entropy doesn't depend on temperature, then when you increase temperature, the point always move left, right? Always move left. Correct, everybody? Is that the case? No, it's not the case. Okay. Let me explain to you because we also need to consider the effect from this term. Okay, the entropy, the entropy change. We know the entropy is dependent on temperature, right? Because you know what? This one is 2. It's a function of temperature. Okay, so but just make the job easier, okay? Instead of calculate term by term to see what's the energy effect, we simply calculate this one, okay? We simply calculate this one. We can simply calculate this term, okay? And since we only talk about the temperature effect, then we just fix that the constant pressure, okay? So how do we do the calculation? We can do the calculation essentially. Okay? So, let me see. Or we can calculate this that way. Or we can use another way to do the job. We can also use this equation. Okay? We can also use this equation. Both work. We can also calculate it, effectively. Instead of calculate that one, we can also calculate this one. Okay, we can see how the reaction constant evolve as a function of temperature. Correct, everyone? Remember, this one is Kp is equals to Pc squared divided by Pa times Pp. If this one increases, the partial pressure of C increases. That means the reaction moving to the right side. Okay. If this Kp decreases, then the Pcp decrease. Okay, that means moving left forward. Okay. So instead, that means we can calculate this one. We can also calculate that one. Okay. But in reality, typically we use this one. Okay, we use this one because in that one we also need to know the information about the mixing, whatever, know the entropy change, whatever, right? But if we calculate that one, we can directly link to the standard the variation of the standard Gibbs free energy. As I mentioned at the beginning, this one is not related to the reaction. It's just related to the intrinsic property of the product and the initial materials, right, or the precursors, right? So instead of calculating that one, we can calculate this term. Okay. Instead of calculating that term, we can calculate this term. Okay, we know that the Kp, we want to know this one, right? We want to know this one, how this one change. But you know that we can make some trick, okay? Instead of calculating this one, it's more complicated. Okay, this one. Make sense? Right. Doesn't matter, right? If the Kp increase, the long Kp also increases. Correct? We can do this term.
Proof this.
No, proof. From this one, you can correct that right? So the question is that how can we calculate this term? How can we calculate this term? Actually, there's one expression that goes to the chapter 7 in your textbook. There's one equation, we call it the Gibbs. We mentioned that one in class. Gibbs-Helmholtz equation. So what it tells us? It tells us the partial G divided by T and partial T, the constant pressure. This one simply equals to minus H divided by T squared. Okay. This one we call it the Gibbs-Helmholtz equation. Go to your textbook and check this equation, okay? You can easily find how we verify it. Okay, basically, it's just from definition of the G equals to H minus Ts. And you divide it by T on both ends, and do the derivative, you divide it. Okay? It's very straightforward. Any questions? Because it's already set P. Think about it. The variation of the G is a function of these T and P, right? We set the P as constant. Then don't need the enthalpy part, involved in the calculation. That's it. It's a very easy job. You can prove yourself. Okay? And then by subtract this equation into this one, by subtract this term with this equation, and we will get something like this. Okay. And we can also mix additional, the adjustment. We can make some more adjustments. So we have okay. Then we have the D on Kp equals to delta H R T squared and D T. Correct, everybody? And then this one equals to D on Kp minus correct? And then we have D on Kp. Okay, we have this relationship. Okay, so we can see that means the long Kp is linearly depend on 1 over t, right? If we plot them in the figure, in the plot, this is 1 over t, okay? And then this one is the long Kp, okay? And the slope is something like this, okay? For example, like this one is the delta H. We have something like this.
How the minus comes?
A minus sign? Okay, so let us briefly discuss this part, okay? So, which end is high temperature? This part is high temperature, or this part is higher temperature? This one is high temperature, right? This is the high temperature, this is low temperature. Okay? That's specific to this case, okay? Specific to this case. So, we don't have that. That's fine. That is, it doesn't matter. Give me a second, let me see how can I draw this better.
There is no C here in this equation. C will be 0.
Let me see.
Y equal to mx plus C.
Huh?
If we consider,
Where is the C?
there is no C and
There's no C. Or there's no C.
long capital.
Huh? No, this is that's for equity.
There is no C.
Why is there a C? You mean the speed of light?
No, no. If we consider y equal to mx plus C, if there is no C constant. If we consider the straight line equation, y equal to mx plus C, there is no C, so it should go through the origin, right?
No, it's a differential. If you do integration, you will have a constant.
So we need to do that first before drawing it, right?
It doesn't matter, I just draw the slope. Correct? It's just a slope.
What is y and x? Okay.
I mean, I just randomly draw something, okay? Anyway, so the, okay, anyway, so the, if you have concern about it, we just draw it, we just remove it. Don't make you confused, okay? Anyway, so we have two terms, okay? Look at that one. So, the, then we need to find the relation between ln Kp and 1 over T, okay? And then from that equation, okay, let's assume if delta H naught is larger than 0. Larger than 0 means what? Means the reaction entropy is positive. Okay? Correct, everybody? So this is the what kind of reaction it is. That means and the final product has higher energy in the initial product, in the initial objects, right? It's absorbed heat. Right? So this reaction is what is called the endo. How to pronounce that one? The endothermic, right? That means it's absorbed heat, right? So if this term is not, if this term is positive, then the entire part is negative, right? Is negative. So that means, so as the temperature going up, this term going down, okay? T going up, this term going, this one going up, this one going down, right? And this one is positive, and this one is negative, right? Then that means the Kp is going down. Correct, everybody? Kp going down means what? Means the reaction is moving to this direction. Correct? That means if the temperature, hold on, I think it's wrong. Temperature going up, Kp, Kp going up, Kp going up. Because it's negative, right? This going down, that one going up, right? Repeat again. T going up, 1 over T going down, right?
Yes.
But this one is positive, that one is not, this one negative, right? So they are negative occurring. So this one going on, this one going up. Correct, everybody? So the reaction actually is going moving to this direction. I'm sorry, moving to this direction. That means if the reaction absorbs heat, we can push the reaction to the right-hand side by increase the temperature, right? And the other thing is the same analysis. If delta H naught is lower than 0, so this one we call the equals X. That means it's release heat, right? Because the final product has lower enthalpy than the precursor. So now T, when T goes up, 1 over T going down, and the Kp going up, right? That means if the reaction releases the heat and you increase the temperature, you're pushing the reaction to the reverse direction, correct? Questions, comments? Everybody happy? Okay.
Actually, but T is, like in both the cases, T is going up, right?
Huh?
In both the cases, T is going up.
Just assume T goes up. Even you can reverse it. T going down, this one go up, this one go down. Right?
Yeah, but this reaction reversibility, it depends on temperature, right?
It depends on temperature.
Yeah, so if T is going up for both the cases,
Yeah. It depends on the whether a entropy change of the entropy is positive or negative. If the change is not positive, that means the reaction need heat.
so then
And if you increase temperature, you give this heat to the system. Then the reaction moving to this direction, right?
so the
and-
next reaction depends on like delta H, not
Yeah.
T.
It
right?
depends on the delta H.
Okay.
Okay. Any other questions? Okay, keep in mind about all the conclusion for the gas. Okay, because when we talk about next chapters, even with involve the condensed matter, condensed phases, we still use gas. Okay, as an intermediate to connect the reactions. Okay. All right, so we move on to the next chapter. Is the reaction. Last chapter is reaction among gas, right? This one is a reaction involving, I probably title differently, but you know what I'm talking about. Condensed phase. So what is condensed phases? Condensed phase means that is in the reaction, the product or the starting material have solid or liquid. Okay? One example. No. For example, we have silver plus oxygen. Okay? We can have something like this. Okay, oxygen gas, silver are solid, and the silver oxide is also solid. So for this reaction, you have to condense. Okay? Or the other reaction, not necessarily to be solid, okay? You can have some reaction like this. Okay? Do you know this reaction? This is why we have the soda, right? Sparkling water. Okay? Anyway, so we're going to talk about that. Similarly, we start a topic from a specific reaction. The reaction looks like this. We have one, I just follow textbook. Okay? We have metal, and we react with oxygen, and we generate the the metal oxide. Got the point? You have two ways to equalize the reaction. You can write something like this, okay? Or you can write something like this. It doesn't matter. It doesn't matter, okay? The reaction constant are the same. The reaction constant is the same. It doesn't matter, okay? It doesn't matter. So but in the textbook, these use this one. You can simply follow the textbook, easier for you to read, okay? But of course, you'll find we only have a different because eventually you know that for the I talked about the gas, okay? The Kp is what? We know that the delta G non equals to minus RT minus, I'm talking about the gas, okay? So one example, it's a Pc squared, Pa, Pb, okay? Just follow the example we talked previously. You can see that this one is what? This one is A plus B, 2C, okay? Of course, you can write the equation in that way. Doesn't matter. Okay? But eventually you will find this term will become half, right? And this one, all terms become half. They just cancel each other. Doesn't matter, right?
Let's see.
It doesn't matter, so it doesn't change anything. Other points? I mean, of course, I mean, this one becomes this. Okay? If you do that one, the definition of the constant become half. Then, basically, you just need to add a parameter here. Okay, you just need a half here. Okay, you still use the original definition of half, but the change of the entropy also become half because you only have half of the original amount of material, so the equation still holds. So that means you don't need worry too much about the parameter in the equation. Okay? That's all the same. So you can use both ways. I know that I prefer use that one, but in textbook they use that one. Anyway, so we just follow textbook. Something like this. That's the reason I really hate this textbook. I have difficult to follow what's talking about. It's always use a very strange angle to cut into topic. I mean, honestly speaking, when I prepare this talk, there's one section I totally don't understand what you want to talk about, and you might try to figure it out. Just one sentence. I will show you. And the other thing that in the textbook, I have no idea which edition you're using. So when I read this one, you're talking about, okay, you also need to compare this equation with equation 7.11. But when I go to textbook, where's 7.11? And I find that 7.7, 7.8, the next page, 7.14.
Yes. Yes, yes.
And that's okay, there's some page missing. But on this one, it's 211. This page is 220. Totally disappeared. Who chose this text?
That equation is not there.
Terrible. That's the reason. But of course, that's my value. If the text is really good, written really good, what's the use of me? Anyway. Okay, so because we have different phases, so in the textbook is also do something else. Okay, to indicate this is solid phase, this is the gas phase, this is solid phase. And that as when we talk about the gases, we know that the equation or the percentage of the accomplishment of the reaction is defined by the reaction constant. Right, by the reaction constant, the Kp. Right, and we know the definition of Kp from gas. But what about the reaction constant in this case? Okay. So in order to know that, we need to calculate. I mean, the definition still works. Okay. We know the definition of the Kp. In that case, but we do not know the partial pressure of the solid phases, right? Typically, I'm not saying that is zero, okay? We have no definition for that, right? We only know the partial pressure of the gas, but we have no definition for the partial pressure of solid, right? And you know that to avoid this problem, they introduced another quantity we call the activity, right? We introduced that one also in the activity actually means how easy can you drag the atom from the solid solution, okay? But the unit is pressure, but it's physically not pressure, okay? But in that case, if you mix with gas, how can we define the pressure of solid? There's no definition, okay? Then the question is, how can we find the reaction constant in this case, okay? So the,
I thought earlier we discussed that the partial pressure of the solid is equivalent to the partial pressure of the gaseous phase.
you just said what I'm going to talk. It disclosed what am I supposed to say? You're right. You're absolutely right. Okay. So that is indeed what I'm going to talk. Okay. So yes, follow the same trick. Follow the same trick. Okay. So we do not know, right? We do not know the pressure, but we can, as I mentioned at the very beginning of the class. So the thermodynamics, if you do not know the process, the detailed process, we can just build our own process as long as these link the initial state and final state. Right? Doesn't matter because we are trying to calculate Gibbs free energy. So we can just artificially create some intermediate steps, right? As the people just said, we can just evaporate this one and evaporate that one. okay, make the reaction happen in the gas phase, okay? At the same temperature and pressure, okay? But for this one, we still use the constant pressure. We have to make the reaction happen at the standard state, okay, 1 atmosphere. Okay? So then we can just artificially create a reaction, something like this. Got it? That means first step, we evaporate both M and MO, okay? And then we evaporate, make the reaction happen in the vapor phase. And then we condense them back. Other points? And the beautiful thing about this one is, under the thermal equilibrium, the chemical potential of this one and the chemical potential of this one will be the same, right? I will adjust that, okay? Because it's under the equilibrium of phase equilibrium. Okay? You are in a reaction, the solid phase of M and the gas phase of the M, they are in the thermal equilibrium state. So the chemical potential of them should be the same, right? Should be the same. In other words, okay? So the other thing is I really hate the M. I have no idea. I shouldn't complain too much, you know? The reason is, in the textbook, they never use the mu, but for all the other textbooks, they always use mu as chemical potential. But they use the G bar on it. Because the molar gives free energy. Molar gives free, you just call it chemical potential. Okay, we have proper name for it, we call it chemical potential. And in the future, even you use something like the chemistry, you're working on the semiconductors, people always say chemical potential. Nobody say the molar gives free energy. The other thing is, the mu will always mix with M. Okay, right now the trouble shows up. Okay, if you cannot distinguish, let me know. I'm trying best to give a good handwriting. Okay, the mu M solid equals to the mu M gas phase. Okay, at this temperature and atmosphere and the pressure. Okay, and the mu MO mu. Yes. Correct? Yeah. Okay, then we can define the reaction. Okay, the reaction. Okay, so it's the delta G, everything under the gas phase, equals to minus RT ln Kp. Okay? And of course, this one equals to not log Kp. Sorry about it. We don't write log. Specific to this case, okay? This is the partial pressure of the MO in the gas phase. Yeah. And P M in the gas phase, and P oxygen, of course, in the gas phase. Square root. Correct, everybody? And once again, on this end, this one is what? This one, we can expand it, right? So this one is the mu MO in the gas phase minus mu M in gas phase minus half mu oxygen in gas phase. Okay? Remember, this is under standard condition. Although the reaction happens at 1 atmosphere, but because the gas are mixture, oxygen, metal, and metal oxide. Okay? So the pressure of the oxygen is not necessarily equal to 1 atmosphere. It's lower than that, right? But for this one, it's 1 atmosphere of the oxygen. Okay? That's the difference between the standard condition and the reaction condition. Okay? Although the total pressure is 1 atmosphere, but the partial pressure of the oxygen not necessarily at 1 atmosphere. Very close. Okay? Very close. Okay. So this one minus RT. right? This is just a definition. And this, I mean, the good thing about, I mean, the reason we're doing this is, whether I know everything about gas-phase reaction, okay? We just want to build up the gas-solid reaction from the gas-phase reaction, okay? By using the condition that, and the thermal equilibrium, the chemical potential of gas phase and the chemical potential of solid phase, they are equal to each other. Okay. But in that case, if we want to calculate, we need to know the gas phase. Okay, the standard condition, the standard, I mean the chemical potential of the metal, but in gas phase. What does that mean? That means 1 atmosphere, okay, and 1 atmosphere. We need to know experimentally, if we want to calculate that one experimentally, we need to know the chemical potential of, for example, when we talk about the ion, okay, we talk about the ion, or copper, or silver. We need to vaporize the silver or copper to a pressure of 1 atmosphere, okay? Think about how high the temperature is. And you need to make the vapor pressure of the metal reaching 1 atmosphere. It's really tough condition, right? Sometimes it's not even experimentally achievable, right? For some metal, yes. For example, like mercury. Okay, you can easily get 1 atmosphere pressure of mercury. Okay, we just simply warm it up. Okay, with the boiled water or whatever, you can easily get that kind of vapor pressure. And in my lab, we have some high pressure mercury vapor lamp. The pressure inside is several atmospheres. But what about ions? What about tungsten? How do you vaporize tungsten? You even cannot melt it, right? How do you vaporize it? Okay. So that means this factor is still like under our imaginary, okay? Although we can, but good thing is that we can calculate. We can calculate. Okay? We still can calculate. Okay. But let me show you how to calculate. We still can calculate. But the good thing is that but ultimately we want to use the solid phase. We want to use the solid phase, right? Because we can measure solid phase easily, right? But for gas phase, it's so tough. The condition we cannot measure. So that means the question is whether we can link the standard chemical potential of the metal and the metal in the gas phase to the parameter in the solid phase under the standard condition. Right now, they equal to each other, but this is in the reaction condition, right? Not necessary to the standard condition. But we need to find a standard condition. Okay, that means under 1 atmosphere. So how to do that? So from this equation, okay, we just take this one as an example. We know this one. The gas phase, this is solid phase, okay? Simply equals to what? Integration of the Cp times dP. Another. We know only the pressure changes, right? The temperature is the same, right? Only the pressure changes. So this one will become dBp. Correct? This solid phase, okay? This is the solid volume, okay? And for the gas, right? So we can calculate this one from the standard condition and add the entropy change due to the pressure change. And for the solid, we have no way to do. We have to do the integration from the definition, right? Correct, everybody? Because you know that basically the chemical potential is just the Gibbs free energy, right? Then the d mu is simply equals to VdP plus or minus SD, right? Since we do not change the temperature, we only change the pressure, then the delta U simply equals to this. But for the ideal gas, we can simply get this. Correct, everybody? And then the argument is like this. The solid typically has very tiny volume, right? Has very tiny volume. contact points have very tiny volume. Then this term, and compare with this term, is very tiny. Okay? In that case, because the condensed phase, the volume is very tiny, right? Think about the single drop of water can fill the other room, right? If you compress the gas to a solid, it's a very tiny piece. But if vaporizing the gas is very, and occupy a large space, okay? Because of that, this one is much, much smaller than this term. Much, much smaller than this term. Okay? And then, because of that, this one simply equals to mu approximately equals to more precisely should be like this. More precisely should be the absolute value. Okay, because this one is negative, this one is positive. Okay, make sense? Then, okay, so let me briefly review the same. So because under the reaction condition, we just build an artificial reaction loop and connect this reaction. And first of all, we evaporate the solid and make the solid into gas, and the gas react with the oxygen. Okay, and generate the metal oxide gas. And the oxide gas will change back to solid. Okay, we just artificially create this reaction. Okay, instead of doing this way, we make the reaction happen here and reaction one and go back. You know what I'm saying? That means the same thing, just like that. When we do the calculation for the engine, we just artificially create the loop to connect the starting point and the final the final destination. Okay? And because of that, we can, under thermal equilibrium, we can use the gas phase, give chemical potential to replace the solid phase chemical potential. Okay? But eventually, we need to change everything back. Okay? And by calculating the difference of the chemical potential between the reaction condition and standard condition, we have the following relationship, right? And then we can know the relationship between the standard gas phase and the standard condition of the solid phase.
So that P is the total pressure of the.
And the partial pressure of the gas. Okay. All right. So because of we know that, we can put this equation back to this one. Okay. So we can replace the gas phase chemical potential with the solid phase. Okay, we know that although we can calculate that one, we have no way to measure it. Okay, but for that one, we can easily measure it experimentally. Okay, just do one by one. The first one is then the solid phase, then the gas phase, then that one is the metal oxide solid phase minus RT log P MO in the gas phase. And then this one is minus mu M solid phase plus RT ln P metal gas phase minus half mu gas phase. Okay. And then this one equals to minus RT ln 1 over P MO G P G and then P oxygen gas phase. Correct? Right? Okay. This one is negative. We have negative sign here. And we can split, expand the log expression, okay? Because the PMO is on the numerator. This one denominator and this one is the numerator. I always have difficulty to say that word.
What is it? Numerator?
numerator.
Numerator, yeah, numerator, yes. It's on the numerator, right? So this one and this one going to cancel each other, right? And this one is positive. This one is on the denominator, and then this one also cancel each other. And you can see the good thing that all the solid phase got canceled out, okay? And eventually, the experiment becomes very simple. We have the mu MO. Correct?
This is expression.
May I read this one? Briefly summarize. Basically, we use this loop to replace the original reaction, okay, to do the calculation. And from this one, we know that the delta G, everything in gas phase, okay, and then we can replace this with delta G. Okay. Is that clear? So practically, we only use that. Okay, we use that. Okay, so we do some the analysis on it. We do some analysis on it. Or we can make this function easier, specific to this condition, but for most of the oxidation process. Because when we talk about materials, we care most about the oxide. I mean, the steel, how the steel got the, oxide or oxygen or whatever. We typically care about this reaction. So in that case, we can also rewrite this one something like this. Okay. We can flip the P power pressure of oxygen. Okay. Any questions? And all right. So this one, once again, is a constant. Okay, it's a constant. It doesn't change. It's a constant. Okay, it's only determined by the chemical potential of the metal, micro oxide, and oxygen under 1 atmosphere. Okay, But this depends on temperature, okay? Standard condition only define the pressure, not depend on temperature, okay? The temperature can change. Okay, so that means if, okay, if we plot it, okay? This is 1 over T. And this one is the ln P oxygen. Okay, ln P oxygen. So we can see that actually, I can do something here. So this one, from this equation, we can also change that to delta G non divided by R, and 1 over T is the ln P oxygen. In this plot, just ignore the order here. Okay, the reason is that you can just move in the front. There's a half difference. Doesn't matter. Okay, doesn't matter. We only analyze the trend. Okay. Okay. So suppose if the delta G non is lower than 0, what does that mean? That means the reaction release heat, right? Release heat. So I'm going to talk about why is release heat, okay? But yeah, then we have something like this, right? Have something like this. Okay, actually, this is the case for water reaction. For example, where in the text we talked about the reaction. The reaction looks like this. So we have 4 moles of the copper plus 1 oxygen, and we generate copper. This is not copper oxide. It's called what? What's the name of it? This compound? Copper oxide.
Acute cross oxide.
Yeah, something like that. Doesn't matter. So for this reaction, the delta Q is lower than 0. Okay? So you can see that if the delta at a given T, okay? More precisely, for this reaction, delta G non is equals to minus 3, 4, 0, 0 minus upon plus. So this reaction gives this kind of the change of gives free energy. So it's basically that means it's released large amount of heat. Okay, it is released large amount of heat. Right? Think about you burn the copper in the air. It releases large amount of heat. Okay, anyway, so look at this one. Okay. Again, which part is high temperature? This one is high temperature. This one is low temperature. Okay. Basically, the ln P non is the reaction constant. 1 over reaction constant. Okay. So you can see that this line actually is defined. This line tells us what? Tells us only on this line we have this reaction. Correct, everybody? Only on this specific line we have this reaction happen. In other words, only on this line the metal, oxygen, and the metal oxide coexist. Right? So the only line we can find this kind of reaction equilibrium, I mean the parameters, right? But what if okay? So and underneath it actually is what? Under this line, this is the state of the copper plus oxygen. And on top of it is the copper oxide. But of course, in the air, we have a lot of oxygen. Okay, we cannot consume all of them. Okay. Below it, the copper and oxide are stable state. And above that one, we only have the copper. What's the name of the compound?
Cube cross.
Whatever. It's CO2. Okay. And only on this range, the reaction takes place. Okay, the reaction takes place. let me briefly then let's go to very interesting, right? So along this direction is very easy to understand, right? If we increase the pressure of oxygen, the copper will become more easy to be oxidized, right? If you put the copper in the pure oxygen to oxidize. If you put the air, probably very slow, right? That's one thing. But along this direction, okay? So if we put this one, this is low temperature, this high temperature. That means with the oxygen as a constant, if the partial pressure of the oxygen is constant, if we increase temperature, this copper will reduce to the copper and oxygen, right? Very weird. But you can do this experiment at home. Okay, you just find a piece of copper got oxidized, burn it on the flame, use a torch and burn it on flame. You will find that copper reduced back to the copper oxide reduced back to copper. Okay, this reaction indeed happens. You know what I'm saying? What's the reason for that? The reason is, as you increase the temperature, if the temperature is high enough, eventually that could become positive. Okay, it's move the reaction backward. Okay, got the points? But you all know that at the room temperature, although the reaction generates heat, but most of the time copper does not got oxidized spontaneously. If you have a shining piece of copper, it doesn't get spontaneously oxidized very quickly, right? So what's the reason for that? The reason is that, again, this one only considers thermodynamics, but doesn't consider the reaction kinetics, okay? Think about it. If you want to oxidize the copper, you need to break down the oxygen molecules to oxygen atoms, right? And then the oxygen molecules need to attack, break the bound of the copper and the oxidizer, right? So quite a lot of, energy barrier in this kind of process. You know what I'm saying? That means although copper and oxygen have the trend to react with each other, but we have a very large energy barrier separate the copper and the oxidized states. You know what I'm saying? But this one can be changed. If you touch the surface with your finger, you'll find the copper got oxidized very quickly. So there's two reasons. One reason is you have some moisture on your fingertip. The other thing is the sulfur. Okay, this is the sulfur. So if you introduce some sulfur onto copper, the copper can react with sulfur very quickly, and you break down the local structure, and oxygen will penetrate into the structure. The same thing for the silver. Okay, you put silver in the air for a very long time, still shining, but as long as you touch it, in a few minutes it got oxidized. You can try. Anybody have silverware? It's very cheap. Any questions? Okay, so right now you know the pressure, right? You know the pressure, okay? You know the pressure. But remember one thing. So on the gas phase reaction, when we change the pressure, we can move, depends on the final product and the initial object, initial materials. It depends on how the pressure changes during the reaction. We can control the direction of the reaction, right? We can reduce the pressure, increase the pressure to move the reaction backward or forward, right? But for that one, if specific to this reaction, if you increase the pressure, it's always move in this direction. The same thing because on this one you have pressure, but on this one you don't have pressure, right? That means if you pressure, you can sit in that way. We just press the oxygen into the metal, right? You know what I'm saying? But when you release it, you extract it out, okay? But this is actually probably not very obvious on oxygen, but on hydrogen, yes. You know that we have the hydrogen storage materials. If you want to put hydrogen in, you pressurize it, the hydrogen will penetrate in the metal. Okay? And if you decrease the pressure, the hydrogen got released back. That's the hydrogen storage materials.
But there is a trick as well. Like I think there is a stable state. Where
Forget about details. The other example is that water and oxygen. How do you make soda? You have to pressurize the carbon dioxide and push it into the water, right? and use a cap, right? You can see that the tank or the bottle of the Coke, they're always pressurized, right? If you open the cap, you can find the gas and comes released. Right? The same thing, right? So any kind of reaction involves this kind of gas and solid phase. We don't worry too much about the, typically the reaction always moves to the right-hand side when pressurized. Okay, so in other words, we don't need to worry too much about the pressure effect. It's so obvious. It's so obvious. Okay, we don't bother to talk about it. But the thing is, we talked about the temperature dependent. Okay. But how the temperature change the reaction? Okay. How the temperature change the reaction? If you go to the textbook is still bothering. I don't know. It's not about half page to do this kind of derivative. I mean, I don't know why they're doing the job. But still, they follow the same thing. You know that we're already mentioning in the gas. Okay. In order to analyze that the reaction, we just simply need to calculate this term. Right? We just need to calculate this term. That's it. Right? By using the Gibbs-Helmholtz equation, something like this. Okay? By calculating this equation, we will know how the reaction change and how the equilibrium chemical reaction constant change as a function of temperature. Right? But the thing that is complicated because we know that the H is the integration of the CPT, right? But this is not the gas phase. It's not gas phase anymore. So we cannot just use that probably 5/3 RT to get to 5/3 R to replace the CP, right? For the solid state and for the copper or metal, typically CP is a function of temperature, unlike the ideal gas, right? Ideal gas CP is not a function of temperature, right? It's a constant, right? It's a constant. But for the solid, it's not the case, okay? So solid, typically CP equals what? We have one expression, not necessary to be accurate, but most of the solid follow this kind of trend, okay? Is that function of temperature follow this kind of relationship, approximate. Okay? It's not very complicated. Think about it. Any kind of curve, you can always fit with the Taylor series.
Is the -2 or?
It's negative. It's negative. Okay. We only keep the linear term and the reverse term. only keep this one. We don't have the 1/t. We have 1/t squared. Okay. So by doing that, I mean, for example, like the metal have this relationship, and the metal oxides also have this relationship. Okay. Also have this relationship. So then the delta H9 is just the integration of delta Cp, right? The delta Cp is defined as the Cpmo minus Cpm. Okay. Then the delta Cp can also be expressed as something like this, right? They follow the same thing, right? Probably M, O. Okay. The A is just like ANO minus AN. B is just BMO minus CN. C is just CMO minus CN. You still follow this trend. Correct, everybody? Then, how many times have we don't spend time on calculation. It's just like very fundamental calculus. Okay? You just do the integration several times, and eventually you will find that delta G9 is equal to BT plus A plus minus delta A AT minus VT squared. That's the result. So the B and A, just the integration constant, right? Remember that we need to calculate the delta H, this one is the integration, right? So this one give us one integration constant. And here's another integration. Okay, that's really have two integration constant, BA, and something randomly distributed. Okay. Okay. Hold on. Something wrong? No. Okay. All right. So this is a theoretical equation. In the textbook, it tells us. We can ignore all these terms. Why was still calculating? And we can ignore all these terms. They're very tiny. And then this one just approximately equal to A plus BT.
Now it looks good.
This is really weird. Why wasting my time to talk about that one in textbook? I spent a lot of time because we don't have time to do this. You see that I do the integral myself last night. So from very top to bottom. And then the textbook told me, you do not need to consider it because you can always ignore it. Anyway. Okay. I need to talk with some more senior professors to see whether they have better textbook. In this textbook, the thermodynamic part is fine, but when we go to like the use the deep spring engine to analyze different systems, it's very chaotic. Okay, anyway. But this is just like experience. For most of systems, you will find it's obey this kind of behavior. For example, we talk about copper, right? At just the right equation, minus 338,000 molecule and plus 138 kT, something like that, right? I just wrote that one. You can see that I also follow one. For the silver reaction with oxygen, follow this one. For the ion, also follow this one. What's the reason for that? I mean, although we know that this is approximation, but there must be a reason why this approximation works, okay? Okay. Let me briefly explain to you, okay? So, look at this reaction. Still, let's talk about this reaction. I think the textbook mentioned it a little bit, but I'm not sure. So let's talk about this. Is solid phase. This is solid phase. This is solid. This is solid. This is the gas, right? We talk about something like the at a given temperature, right? So we know that the solid has the interaction between atoms is much stronger than gas, right? That's the reason this is gas is solid. Correct, everybody? Then the form of the solid state chemical bond dominate the change of the entropy, right? The solid bond formation dominate. Correct, everybody? Of course, we still have the entropy from gas, but it never have very small, contribution. Because the interaction between the gas molecule is very small, right? But the solid have very strong interactions, right? They have the metal bond, they have the covalence bond, whatever, right? But you know that this one is not very sensitive to temperature, right? This one is not very sensitive to temperature, okay? The metal, you warm it up, cool it down, it's still a piece of metal. Because the distance between atoms doesn't change that much, so the energy doesn't change that much. Unless you go above the melting point, right? On the other hand, this one has the dominating entropy. Correct, everybody? This one has the dominating entropy. Okay. Basically, when it's got to react, all the entropy from solid got consumed. Entropy gone, right? We don't have this term anymore, right? You know what I'm saying? Because in the solid, we can ignore the entropy of the solid, but the gas has the dominating entropy, right? That's because of that dominating entropy, but we need to unify we only need to consider these two factors, right? Then the delta G simply equals to delta H plus T delta S. That's it. Okay, you can see that we have this kind of relationship, right? And you can see this term basically is the entropy due to the solid state reaction, and this one is entropy of the solid state reaction, and this B is simply the entropy of the gas.
Why is it plus instead of minus?
Oh yeah,
What's the switch?
it's minus. It's minus. But there one, the B can be negative and positive. Okay? Yeah, it's negative. Make sense? Does that make sense? Okay, so I will still have some left over. Because of this relationship, we can introduce another concept. We call it, I mean not concept, it's another technique. Okay? We call it the Allingham diagram. Allingham diagram. So what it tells us? We have this relationship. Right? So the delta G non equals to A plus BT equals to what? RT ln pressure oxygen. Remember that when I'm talking about the example, I have a 1/2 as the order here, but can simply absorb that one in A and B, right? It's just a half, and then we just double A and B. Doesn't matter, okay? The relationship is still there, right? And by using this equation, we can find when the oxygen reaction, at what temperature the oxidation reaction happens. Okay? We already mentioned when the R and the P located in that curve. Remember that curve I drawn previously? If that R and P located on the curve, that is where the reaction happens. If it's on either side of the curve, it's either metal and oxygen or the metal oxide, right? So in that case, we can use this equation. If we know the pressure, we can use this relationship to determine the reaction temperature. On the other hand, if we know the temperature, we can use this equation to find the partial pressure of oxygen, which can give us the trigger reaction. Okay? So basically, for example, if P oxygen, this is partial pressure of oxygen, okay? It's 1 atmosphere. Okay. If the partial pressure of the oxygen is 1 atmosphere, then we have something like this. Remember? So then the delta G non equals to 0, right? This is 0 because the P is 1, right? Okay. And we will have something like this. Okay? So this curve is A plus B T. Okay? It depends on the sign of A and B. Okay, I just randomly draw a curve. You know what I'm saying? And then this one, this temperature, this is the T, okay? This is the delta G naught, okay? And this one is 0. And this temperature tells us the reaction temperature. Okay? Got my point? And what if the pressure of the oxygen change? And for this specific line, the P oxygen is simply equals to 1 atmosphere. It's just a 0 straight line. Okay? But what if the P lower than 1 atmosphere? We just put it here, then this term become negative. This term become negative, right? And then this is not straight line anymore. It just like become something like this, right? And then as the pressure going down and down, the curve moving downward, but it's not a linear line. And by finding this kind of cross point, you can tell the reaction temperature. That's it. Basically, you just solve the problem. You are solving the equation by drawing the figure. Okay. So this figure has a special name called island. Check the textbook. Okay, they make the job more complicated. But I think this is an easier way for us to explain the concept. Questions, comments? If you have any comments, next time we're going to do some practice. Okay, so I can help you to clarify how to use this kind of knowledge.
Class is next week Thursday, right?
Huh?
Class is next week Thursday now?
Oh, there's no Tuesday class? Oh, why? Lunch day. There are only one break during semester, very exhausting. Where is the hurricane?
When temperature increases or decreases, it becomes
No, temperature parameter. No parameter beyond 1 atmosphere, this one is positive. So it's
Oh, okay. So when pressure decreases, it becomes negative.
It's over. Yeah. All right. See you around. Have a good one.